Thank you, Karsten, for the introduction, and welcome everyone to my talk today. My name is Razan Altarabeen. I'm a PhD student in Technical University of Hamburg, and today I will talk to you about one of our projects. And as you can see here, it's named HLBhybrid, Entwicklung innovativer Fassaden-Sandwichelemente unter Verwendung von Holzleichtbeton und Smart Materials als Dämmstoff. So this project was, or is actually still coordinated with Technische, Hochschule Nürnberg and other industrial partners. And I will start with the motivation of this project. So the motivation of this project is to produce a non-loading thermal insulating facade elements that are slim, so space-saving, also stable and commercially compatible, and that also offer advantages or added functionalities. My part in this project was mainly on developing the lignin aerogels as sandwich elementin, which would be a part of this facade components at the end. So just to start, some of you might not be familiar with the term of aerogels. So aerogels are these new, relatively new materials, we can say. Basically, they are very lightweight and have a high porosity that can go up to 99%. So you can say that there's just air inside. And they can be produced from different materials. So the gels can be produced from either organic or inorganic materials. And therefore, they can also be used in different industrial applications, with either thermal conductivity or thermal insulation, or food materials, or even drug delivery, and so on. So what is the stand of the art in our research institute in TOHH? So where we are at, we right now can produce 6 liters per batch. We are producing the aerosols through the supercritical CO2 extraction and high pressure processes, and we are very advanced in the particle production of aerosol technology. We are also in the research, we're also focusing on modeling and the scaling up of the production process of the aerosols. We're also very much invested in developing new types of aerosol materials that meets the industry applications. And we are also having a look at the absorption of different components inside the pore structures of the aerosols. And of course, we are investigating the thermodynamic phenomena that governs the aerosol production processes. So we are very familiar with the whole aerosol production process, either from the material design up to the scale up. And our part in the HLBhybrid project is mainly to produce bio-based, multifunctional, porous materials that can be used as facade elements. So this overall project or overall objective can be, divided into more smaller objectives. The first objective was to choose a biomass or lignin type that is suitable for our targeted application, which is the thermal insulation. And the second objective, as you can see here, is to optimize the bio-based nanoporous materials from the chosen biomass from the starter. So basically, in other words, to go from here to here. And let's now move to the experimental part. So I would like just to explain shortly why lignin, why this hustle about lignin that you might have been hearing about lately. So as you might know, lignin is the most abundant biopolymer in nature, comes right after cellulose, as we heard before. And when we look here at the molecular structure of the lignin, we can see that it has an aromatic structure with various functional side groups, which gives it diverse functionalities. Lignin can be found in nature in different plants, so it's usually the component that gives these plants the rigidity or the mechanical stability, so to say, but it's also widely produced as a byproduct in the paper and pulp industry. Nonetheless, lignin is not fully utilized. Its functionalities has not been still exploited. And the reason for that is when the lignin has this complex and undefined structure, which changes when we choose the type of biomass. So if we go from wheat straw to Bombay or a different plant, we would have a different structure at the end. And even if we change the extraction process, we would result in a different lignin. So that being said, different biomass sources, different processes result in different lignin molecular structures, which results in different behavior. So the behavior of lignin is unpredictable and not completely understood yet, which delays its utilization into the industrial applications. So for this reason, what we did in our project is that we collected 30, or let's say 23 types, if I want to be honest, 23 types of lignins from different processes, as you can see here, and different biomass sources. What we did is first characterize them in terms of their particle size, in terms of their ash content, and class and content. So class and content is just an indication of their purity. How pure is our lignin? Does it have other contaminations or cellulose or hemicellulose? And also, we had a look at the functional groups, as you can see here. All these properties were taken into consideration beside other important factors, such as the commercial availability and compatibility. So how expensive is our lignin? Is it available? Can we get it in industrial amounts or not? After all these points I've mentioned earlier were taken into consideration when deciding which lignin to go for. And based on that, we have chosen the soda lignin here from wheat straw. So after that, this soda lignin was utilized to produce the lignin aerogel particles. And as you can see here, this is done through first adding the lignin in its particle form, in its pure form, no chemical modification whatsoever. It's added to the alginate solution. And then this solution is just dripped into an ionic bath inducing the gelation process. Then we have the gels, as you can see here in this photo. These gels have just water inside. So the next step is solvent exchange, which is important to have a more suitable solvent that can be used for the supercritical CO2 extraction process. It can be either ethanol or acetone. And then we do the supercritical CO2 extraction at 120 bar, 60 degrees. And then we have this very nice porous structure, which we call aerogels. Later on, the lignin alginate aerogel particles are characterized in terms of two important properties. The first property is the volumetric yield, which is an indication of or let's say it's a ratio of the final volume to the initial volume. So it's just an indication of how much your gel was able to retain its volume and how much it is mechanically stable. And if we look here, we can see that lignins from 40% upward showed a higher mechanical properties, and they were pronounced with a higher volumetric yield at the end, up to 80%. The second important properties when talking about aerogels in general is the specific surface area, which is just an indication of how much you have specific surface area inside and how much your material is porous. So if we look here, we can see that this is the lignin content from 0 to 80, and this is the specific surface area here on the y-axis. And we can see when we go up with the lignin amount added to the aerogel, we have less specific surface area. And this is because that the lignin you add to your aerogel adds to the mass of the aerogel, which results in lower specific surface area per gram. Nonetheless, we can already conclude that the lignin actually disperses itself into the pore structure and enforcing the mechanical stability of the aerogels. Next was actually to develop a prototype from these lignin aerogel particles, the ones I showed you before. And this part was done in cooperation with Hochschule für Technische Wirtschaft and Kultur Leipzig. This is still work in process, but what we did basically is that we took the particles you can see here, we melted them down and pressed them and had a look about on the compressibility and the pressibility of the particles and what are the resulted parameters. So usually when we talk about the pressing, we have a problem with the elasticity of the material. So usually when dealing with non-organic aerogels, they use fibers as additive to get rid of this problem. In our case, what we did is, as I told you, these steps I've showed before, we gelated the polymer, and then we did supercritical CO2 drying process. Then these, how the particles look after the drying. They are sent to Leipzig, where they mill them down in a household mixer, and then they press them with different pressing pressures with these dimensions. So what we saw is that with lignin, we were able to press the aerogels without the need of the fibers, and they were mechanically stable in comparison to other aerogels that were pressed in the same manner. And next, what we did is we tried to evaluate the mechanical force stability and the thermal conductivity. So the properties you can see here are actually for the 8% sample, which unfortunately I don't have with me here, but it's 11 by 11 centimeter. Today I brought a different, this one is 32, I have with me here, and you can see later on. So what we saw is that using different pressure values, or pressing pressure, let's say, to be accurate, we are able to get thermal conductivity from 23 to 40, and with a density of 0.075 to till 0.25. This really depends on the pressing and how much you would require a pressing pressure to reach a certain mechanical stability of the final plate. So what still needs to be done? As I've mentioned before, the prototype is still in progress. We're still trying to evaluate other properties that are important. And for example, the moisture uptake. So we know that the moisture uptake is always a problem when it comes to aerogels, and it has to be measured. It's also very important and interesting to look at other functionalities that the lignin can provide beside the mechanical stability, which are the flame retardancy. So we know that the lignin has this aromatic structure, and when it's being subjected to a flame, it would char, resulting in this flame retardancy behavior, which is also important for the facade elements. We would like also to optimize our prototype further, maybe have different layers with different thicknesses and densities and so on. What we are doing right now at THH is that we are trying to optimize the particle production process. So we have it in a more of a continuous manner, and we try to reduce the drying time down to 5 minutes, which means lower cost of the whole production of the lignin aerogel particles. And this brings me to the end of my talk. Thank you for listening, and you can have any questions. Then I have
Danke, Frau Altarabeen. Hat jemand aus dem Publikum vielleicht Fragen? Fragen können auf Deutsch, Englisch gestellt werden. Ist ganz offen.
Hallo, Simon Schmidt von Frau EWB. Ich würde die Frage auf Englisch stellen, wenn es in Ordnung ist, oder Deutsch?
Wie du willst.
Okay.
We try.
Okay, so then in German. Ich habe mich gefragt, wie groß die Partikelgröße der Aerogele ist, wenn ihr die aufmalt. Dann zerstört ihr die ja eigentlich, oder?
So it's 2 to 3 millimeter in diameter, but of course, as I've mentioned, this is when we do the pressing, we have to mill it down further.
Yeah, but in that process, you're cracking up the balls.
Yes. In the process, we are just doing 2 to 3 millimeter, but of course, we can control the size of the particle. This is not a problem.
Okay.
So thanks. We can do also jet cutting, where we have very, very small particle size.
Okay. Thank you.
Noch weitere Fragen? Dann hätte ich vielleicht noch eine Frage. Wie gehen Sie auch mit Feuchtigkeit um im Dämmstoff?
Right.
Feuchtigkeit, humidity?
The humidity. We are actually still testing it, but the problem with the aerosols is that when they have this moisture uptake, is that the pores might collapse. So this is something we have to investigate, and also in terms of how much we add lignin to reduce the moisture uptake.
Thank you. Wenn es sonst keine Fragen gibt,